Okay, well, welcome back, everyone. To change gears, we're going to be going into ocean modeling now. And so Gustavo Marquez was actually the tutorial chair last year. So he's had a lot of experience in this role. You're the liaison for the Ocean Model Working Group, that's correct? Yeah. And he's been fundamental in terms of getting the transition from POP to MOM going. I'll let Gustavo take over and give you some ideas about ocean modeling. Thanks, Gustavo.
Peter. Good morning, everybody. I'm a physical oceanographer by training, specialized in ocean modeling. I'm project scientist in the oceanography section here at CGD. So I'll give you a perspective of the basics of ocean modeling, starting with what are the challenges, some ocean properties, the governing equations, boundary conditions, then the types of grid, horizontal and vertical, how we couple with other components really briefly. Then I'll very quickly mention some of the characteristics of the two ocean models that we're using. So the parallel ocean model version 2 POP, which is the ocean model that you guys are using on the practical at the moment. And then I'll touch upon I'll mention briefly about the modular ocean model version 6, or MOM 6 for short, which is the new ocean model that we are transitioning to. And I'll provide you some helpful resources. Tomorrow, Peter Jen will focus more on the parametrizations that we use in the ocean model. So today I'll stay with the basic concepts and I'll give you a general overview. So let's jump right on it. The most, or I guess the order one challenge in ocean modeling is the fact that the ocean or the land boundaries are very irregular. And I'll try to play this animation for you guys. How do I do that? Oops. Wow, it took me to YouTube, all right? So this is the perpetual ocean was done with MIT GCM. And the idea here is, these are the ocean currents, the surface currents, just to pay attention on how complex they are, like how the land is playing a crucial role in kind of dictating how the currents look like. For example, between Mexico and Cuba, like the current has to flow with this narrow channel and then creates this meandering and then kind of flows towards the Florida Straits, and then the Gulf Stream. Now we're moving to the equatorial region in the Atlantic, a lot of eddies. Now to the tip of Africa, so you see the so-called Agulhas rings. Look, they're formed between Madagascar and Africa, and then they kind of propagate towards the Atlantic. Now moving to the Indian Ocean. So I'll let you, I put the link for this animation on the PDF, and you guys can take a look afterwards. So just pay attention of how the irregular boundaries play a key role in dictating how the ocean currents look like. Now we can go back to the presentation, please. Thank you. This plot is showing the time scale in the y-axis versus the spatial scale on the x-axis. And you probably have seen this kind of plot before, is in a logarithmic on both axes. And then the balloons show kind of different processes happening. So if you go from the bottom left, those are the smallest and fastest, for example, capillary waves. To the top right, those are the long and large, for example, climate change, El Nino. So I'm highlighting all these processes happening between the two of them. There's a lot of things going on. And now in green, these are the typical resolution, both spatially and temporal, that we resolved with the 3-degree ocean model, which is a low resolution ocean model. So we can capture some of the climate change, like, because the resolution is low, we can run for thousands of years. We can observe El Nino, some Rossby waves. And then now in black is the workhorse 1-degree configuration, which is what you guys run on the practical example. So now we're able to go a little bit to the left and capture more spatial scales, a little bit of the eddies and fronts, but no, just very little of those processes. Now the high resolution grid that we have, which is a 1/10 of the degree in red, now we're starting to capture most of the eddies, but a little bit of coastal upwelling, and just touching on like mesoscale and shorter scales and physical biological interaction. So the bottom line is with ocean models, we can simulate the climate. If we do the same exercise with the atmosphere, and now again, with the typical workhorse configuration, 1 degree in the atmosphere, we are capturing most of the mesoscale with that, including tropical cyclones. So 1 degree atmosphere, we can simulate the weather. 1 degree ocean, we can simulate the climate. That's the big difference between these two components. And why is that? Well, I'll get on that on the next slide. But first, the bottom line is when you use an ocean model for climate simulations, we need to come up with parameterization. So on the left is the 1/10 of degree simulation for a day, and we're looking at SST. So this is a day in 2000, and we're looking at the tip of Africa. So those are Agulhas rings that we saw in the animation, and we can see the Agulhas rings like playing its reflection on the SST. So you see these blobs of SST moving to the west. And if you look on the right, this is the same plot for a 1 degree on the same day. And we don't see those eddies. So we need to represent, on the 1 degree, we need to represent the effect of these eddies. And how we do that, you will learn more about this specific type of parameterization tomorrow with Peter Jen. So the mixing associated with these eddies needs to be represented in the low resolution model and must be parameterized. So going back to the difference between the ocean and the atmosphere, the changes in density from the top of the atmosphere to the bottom of the atmosphere are much larger than in the ocean. And that affects the so-called Rossby radius of deformation, which is given here. So N is the Brun-Weishaler frequency, H is the vertical dimension of the domain, and then divided by pi, F is the Coriolis parameter. So in the ocean, the first radius of deformation is on the order of hundreds to tens of kilometers, while in the atmosphere is an order of magnitude larger. Therefore, like you need less grid spacing to represent, or you need with a coarser resolution grid spacing, you can represent better the mesoscale processes in the atmosphere compared to the ocean. And to give you an idea, this plot is from Halberg 2013. It shows the ratio between the baroclinic radius of deformation divided by the grid spacing. So you can, just to give you an idea of like how much resolution in the horizontal is needed to start resolving the mesoscale eddies. So in the equator is on the order of between 1.5 of degree, like that, and it's really showing here. The radius is like 2 delta x, so two times the grid spacing. And in reality, we need like at least six times. So you need within 1 radius of deformation, 6 grid points in order to resolve well the mesoscale phenomenon. So it's even worse than what's shown here. But the bottom line is on the equator, you need order of like 1/2 of degree to start resolving the first baroclinic of deformation, while at high latitudes, like it's kind of off the scale here is like less than 1/50 of a degree. 1/10 of a degree, you can resolve the mesoscale mostly everywhere, but still not at all locations, especially high latitudes and shallow. Another challenge in ocean modeling is that once the water masses are formed and they sink below the surface, there's very little mixing that happens between them. And that's why we can name the water masses. You've probably heard of Antarctica bottom water, North Atlantic deep water. And this is actually a challenge in terms of representing ocean with computers, because any numerical spurious mixing will affect your solution a lot. So like, you need to, once the water masses are formed and they sink, there's again very little mixing that happens, and any spurious mixing because of your numerics will affect your solution, especially in climate simulations. Another challenge is because the deep ocean, there's like little mixing, you can use a simple scaling argument to estimate how long it will take for the deep ocean to equilibrate. So if you take like typical vertical scale of the ocean, like the typical depth of the ocean on average is like 4,000 meters, you square that, and divided by the vertical diffusivity, like typical vertical diffusivity used, you get a 20,000 years. So that's approximately how long it would take for the deep ocean to equilibrate. That's a lot of time. In contrast, if you just look at the dynamical adjustment time, so how long it takes for example, a non-dispersive long Rossby wave to cross the ocean basin, and here I'm using this the dispersion relation for this kind of waves given by C sub R. And if you take the Pacific Ocean as an example, it will take approximately 2 years for this wave to propagate, which compared to 20,000 years is very fast. But compared to the atmosphere, like how long it takes from front to propagate, 2 years is very long if you do an analogy with this same kind of phenomenon in the atmosphere, which is much faster. So the bottom line is that performing climate simulations or long climate simulations with at resolving or permitting models is impractical because we need a lot of resolution. Therefore, we tend to use a resolution that requires parametrizations, especially for these long simulations. The spurious mixing in the ocean is a big deal and can significantly degrade the solution. So when we design ocean models for climate simulations, we have to be very careful with that. And we must live with the ocean not being at equilibrium. That is, very rarely you see a simulation that was run for thousands of years. It's mostly done for paleo, and those tends to be very coarse resolution. And another thing that I didn't mention is that the heat capacity in the ocean is much larger than the atmosphere. That's it's a big deal because the ocean is an important reservoir for heat. So the ocean is taking all the excessive heat that is being given by climate change, and how will that affect us? We're still trying to understand that, but all that excessive heat is being accumulated in the ocean. And because of this, the ocean has the memory for the climate system and has a lot of implications for things like decadal prediction and so on. Okay, so now moving to the equations governing the ocean. I'll try to simplify as much as possible. I'm kind of giving you a general sense here. Keep in mind that there's a lot of details that are not included here, but I'm happy to talk afterwards with those of you interested in going into the weeds. So we have 7 equations and 7 unknowns. So we have 3 equations for velocity, u, v, w, 1 equation for potential temperature, 1 equation for salinity, then density, which combines both potential temperature and salinity, and then pressure. So with 7 equations, 7 unknowns, we can solve this system. Plus, if you have other traces, for example, CFCs, ideal age, then you need a separate equation for each of those. The approximations that are made when we design the ocean models are, the first one is a thin shell. Basically, the depth of the ocean can be neglected when compared to the radius of the Earth. And that leads to simplifications in the Marino variation in the zonal variation of the Coriolis parameter. So we only consider the curvature effect in Coriolis on the meridional direction, not in the zonal. The Boussinesq approximation, which is a big deal, basically the changes in the density in the ocean are very small when compared to the mean density. And that's what is given here. So rho, you can approximate rho as rho null plus rho prime, where rho prime is much smaller than rho null. Therefore, everywhere in the equations, but in the hydrostatic approximation, we can replace rho by rho null. Continuity equation, so basically incompressible flow. So what flows into a control volume, what flows in must flow out. So it's the idea of constant volume in the ocean. And then finally, the hydrostatic approximation, which basically all the vertical accelerations that are smaller than gravity are neglected. And for climate ocean model using climate simulations, this is a pretty good approximation. If you go more into coastal ocean modeling, then this starts to break because then your horizontal and vertical scales become more comparable, and things like Kelvin-Helmholtz instability, you can start to, it becomes more important and you can start to represent them. But in a global climate model, you cannot represent things like that, like this type of instabilities. That's why the hydrostatic approximation is a good one for this case. So jumping into the equations, this is the equation for horizontal momentum in vector form. This is the vertical momentum or hydrostatic approximation. So basically partial E partial Z equals minus rho G. Mass conservation, which is on 3A. So that's the full form of mass conservation. But because we make the hydrostatic approximation, that simplifies into the continuity equation, which is given by 3B. The transport of temperature. And by the way, I'm neglecting the sources and sinks on the right-hand side here. So no, like the same for the momentum equations, you have like the forcing at the surface is not included here, but I will talk about that a little bit. So this is for temperature. Similarly for salinity, the same equation. And then finally, equation of state, which is a nonlinear equation where we combine salinity, potential temperature, and pressure to give you density. What are the boundary conditions? So starting from the ocean surface, there are flux exchanges at the surface, for example, momentum, the wind blowing on top of the ocean, also heat and fresh water. So heat goes into the temperature equation, fresh water goes into the salinity equation, and mass. Important to note that in the POP model, the one that you guys are using, there is no freshwater flux. And instead, we do something called virtual salt flux. So if rains on top of the ocean, instead of throwing fresh water into the ocean, we take or put salt, depending on if you're throwing water, if you're diluting the ocean. So we will remove salt to kind of mimic what was happening if you were diluting the ocean. It's only in POP. In MOM uses the so-called natural boundary condition where you can actually put water, add water. In the ocean bottom, we have no traces flux through the bottom. There is an option in MOM to represent geothermal heating, but we're not exercising that at the moment. And the normal velocity is set to 0, and then we have a quadratic bottom stress. Then the lateral boundaries are no fluxes through the boundaries, and the flow normal to the solid boundary is set to 0. And there's also no slip boundary conditions at the sides. Now moving to the type of horizontal grid staggering used. I'm going to present you two because the two models that we are working on have different staggering, starting with the so-called Arakawa Big Grid, which is shown here. So at the center of the cell, in the letter T, those are tracer points. And then the corners, U and V, that's where we represent the velocity points. So no, they're not on the same point, they're kind of collocated. This is a top view. And the advantage of this grid is that it naturally fits the no-slip boundary conditions. So U and V on the same point is easy to say, oh, this is land. So it's supposed to be 0. So imposing the no-slip boundary condition is easier on this grid. It has a better dispersion of the Rossby waves at coarse resolution. So again, those paleo type simulations that have very coarse resolution, 3 degrees or so, the big grid has advantage over other grids. And also has the smaller truncation errors in the computation of the Coriolis term. So that's the minus VU and plus minus FU plus FV in the momentum equations. Because U and V are on the same point in this grid, we don't need to do interpolation of the components to calculate the Coriolis term, which is helpful and leads to smaller truncation errors. The disadvantage is that we cannot represent, first of all, we cannot represent single point channels. So as shown in the schematic on the right, the green squares are land, the blue are ocean. In order to have a channel that the water flows through, you need to have at least 2 grid points. So 2, as shown by the 2 capital T here. Otherwise, the velocity points will always be on land and you will not be able to flow through that channel. And it also has larger truncations in the pressure gradient terms. So as I mentioned before, this is the grid that we use in the POP model that you guys are running right now. The other grid is the so-called Arakawa C grid. And so again, the tracer points are on the center, but now U and V are collocated. So U is on the side of the tracer points and V is on top and bottom. Again, this top view highlights that. And what is the main advantage of this is that you can now simulate the flow through a channel using a single grid cell. Because even though U will be masked, like let's say you have land on both your left and right side, the U points will be masked. You will now have a zonal flux, but the V points will be ocean, and you'll be able to flow through the channel. And then the disadvantage is kind of the opposite of the advantage of the other one. So there is the Coriolis terms. Now you need to do interpolation because U and V are on different locations, and then you have it's less accurate than in the big grid, and it also has not as good dispersion relations for the Rossby waves at coarse resolution, so like 3 degrees or so. And this is the grid used in the MOM6 model. The choice of vertical coordinate systems in the ocean model. So this is a very important topic of research, and when you're designing the ocean model, your choice of vertical coordinate system makes a huge difference. And I'm going to list you like 3 different coordinate systems that are used. Like most of the models use the Z coordinate, so the first one on the left. The main advantage of this coordinate is, so this is basically your coordinate is a function of depth. And you can specify the resolution on the water column where you would like, and that resolution will be fixed throughout the simulation. The advantage of this is like locations where you have a lot of mixing, so near the surface, you can put a lot of points there and represent the processes happening there well. The disadvantage, however, is that as you go near topography towards the bottom of the ocean, then you start having a lot of the grid spacing between two interfaces. The distance between 2 interfaces becomes large, and then you don't represent the dynamics close to the bottom very well. You can argue that if you have a lot of grid points, then you can make a good resolution near the bottom as well, but then your model will become very computationally expensive. Another advantage is it's much easier to work with equations in the Z coordinate system. The second one on the middle is the so-called sigma or terrain following coordinate. This is mostly used in the regional modeling community. So in this case, the coordinate is following the topography. Notice how the lines are kind of following the topography. Again, it's nice now because you can put the resolution you want, so you can increase resolution near the bottom, near the surface. But the main downside is that you tend to have a lot of pressure gradient errors near steep topography with this type of coordinate system. And again, if for climate simulations, if you have any spurious mixing, you degrade the solution a lot. So therefore, like you rarely see ocean models used for climate simulations written in the so-called sigma coordinate. And finally, on the far right, these are the isopycnal coordinates. So basically now your coordinate is a function of you being your coordinate in terms of density classes. So for example, the first layer can be potential density, and we tend to use the potential density reference to 2000 decibars, but you could use to another pressure level. And then your layers have constant potential density, and you can then spread how you want to divide it, how you want to beam the density to create your coordinate. The main advantage is, again, now once the water masses form and they sink, they tend to mix along density surfaces, and this type of model will let you very small spurious mixing because it's a natural coordinate of the model. However, near the surface where you have a lot of mixing, then this is the disadvantage of this model, because you need to combine that with a mixed layer model in order to represent, for example, the mixing with the surface, so from heating, cooling. So in reality, like we would combine all of the best of all of these and create a grid. And that's what has led to the development of the so-called hybrid coordinate systems, which is, we have this capability in the new model MOM6. And again, I want to emphasize that the coordinate system in ocean model is an area of very active research and development. Now, focusing on the grids that we are using. So on the left are the MOM6 vertical grids. So the top is a Z coordinate. So I put Z star. So Z star is a class of the Z coordinate. Is this kind of the same idea? We have 65 levels. this is just a section of temperature, and the lines represent the vertical grid. Then the bottom is a hybrid coordinate, is a Z star near the surface. So you can see near the surface has a lot of resolution, and then below a certain depth or a certain density class, we start to transition to a density coordinate. And on the right are the pop vertical grids, which are all Z star. The ones you guys are using are in red, has 60 levels. So that's the grid used. We tend to have high resolution near the surface, and that kind of decays exponentially with that. In terms of surface forcing options for the ocean model within CSM, we have basically 3 comp sets. You guys are using the B comp set or fully coupled mode. So all the components are active. But in the ocean, we also tend to, when developing, especially use all the comp sets. For example, the C comp set has only ocean active. Everything else, all the other fluxes are given by a data component. And the one that we use the most in the ocean, besides fully coupled, would be the so-called G comp set, where ocean and sea ice are active. Everything else is given by data. And then the forcing protocols, we have basically 2 different protocols. The first one is the core forcing. I'll let the details here for those of you interested to look afterwards. And then more recently, you're using the GRA 55 protocol. In terms of coupling, how the ocean communicates with the other components. So that's it's a big deal. So how do you, if the ocean is communicating every hour, for example, with the coupler, the atmosphere is communicating half an hour, the land model every 3 hours. How do we make all of things happening and more importantly, the important properties being conserved? So that's a big deal in CSM and all other climate models. And the way we do is, they can run with different coupling time steps. And I think one of the exercises yesterday asked you to change the coupling time step of the atmosphere. And the coupler can take care of making sure that things are conserved between when you migrate from one to another, when you pass a flux from the atmosphere to the ocean and vice versa. So out of the box, the atmosphere is coupled every half an hour. The ocean is coupled every 1 hour. But again, we can change that, and the coupler is there to make sure that it doesn't matter the values, things will be conserved as you go from different values of coupling. I'm putting the ATM and ocean here, but the same applies for land, sea ice, land ice, and etc. All right, now moving into the POP model. So as I mentioned before, this model is a Z level or it's a Z coordinate model. It was initially developed at the Los Alamos National Laboratory. It resolves the 3-dimensional primitive equations in a general orthogonal coordinate in the horizontal with the hydrostatic and Boussinesq approximations. It has a linearized free surface formulation used for the barotropic equation and for the surface pressure. The global integral of the ocean volume remains constant, so that's a consequence of the Boussinesq approximation. And also because we have the freshwater fluxes are treated as a virtual salt flux, so using a reference salinity. So this is a particular to this model. The new model will not have that approximation anymore or that limitation. These are the grids used in the POP model. The first one is the one you are using, is this displaced pole. So notice that the pole, instead of being in the middle of the Arctic, has been displaced to being on top of England or Greenland. So removes this singularity from happening in the ocean, because otherwise, it's a problem. All the cells converge into a single point. So the GX one is the workhorse grid that you guys are running. We also have the GX3, which is the 3-degree version that's used mostly for testing in paleo. And all of them have a equatorial refinement. So near the equator, we tend to increase the resolution to represent the equatorial processes better. The other grid used with POP is the so-called tripole grid at 1/10 of a degree. So it's nominal 1/10. It's eddy resolving mostly almost everywhere. If you're interested to learn about the different grids in more details, not just about this was used in CSM, but in general, I'm putting a reference here from this Murray 1996 paper, which describes all the types of grids very nicely. Switching now to MOM6, so the new model. So this is a finite volume solver. It has the hydrostatic approximation or it has the Boussinesq approximation or the non-Boussinesq, so you can run in both modes. The advantage, out of the box, you run on the Boussinesq mode. If you would like to run on the non-Boussinesq mode, that's mostly for things like studying sea level rise. So the non-Boussinesq let you understand the effect of the ocean on sea level rise in a more complete way. And the main advantage of this model, or the main capability, is the option to use this so-called arbitrary Lagrangian Eulerian coordinate system. So it's a vertical coordinate system that lets you choose of anything you want. It can be a Z, it can be a sigma, or it can be a combination of both. The plot on the right shows basically is a sloped ocean, and you put dense water on the top of the slope, and you let the dense water flow as a gravity current. And that is simulated with 3 different coordinate systems, Z star, sigma, and rho. And you can see how that plume flowing down slope differs significantly between the coordinate systems that you choose. Just to give you a sense of how that choice, which again is a very important choice in ocean modeling, matters for the problem. One of the advantages of this coordinate system is you have no vertical CFL limit, because basically your grid is moving up and down, the thickness of your grid is moving up and down depending on the convergence and divergence of the horizontal flow. It has the option to subcycle gravity waves, and another very nice capability is the built-in wet and drying, which I'll show an example in a second. So things like, for example, a wave pushing into the shore, and then coming back, like with tide, so making the land point wet or dry. In this model, that capability is built in. Unlike the POP model, which kind of the development was centralized, was focused on just on a few places, the MOM6 model is an open development concept. So anyone can develop the model. You can clone the model now, and if you see an error or something that you'd like to improve, you can create a pull request and then submit your contributions, and it's open to anyone. And we have tremendous support from GFGL. We have weekly meetings with them. Not just NCAR NCAR is not the only center using it. There's centers throughout the US and also overseas using that model, and we all communicate with each other. The development is via GitHub. Again, is a growing community of users, universities, labs. And the way we do is there is a central repository called the dev main repository. And then each center has its own fork of that. For example, we have one here, NCAR. And then every month or so, we all communicate with the main repository and get the features that other people have developed in other places, and vice versa. Now moving to the choices of parametrizations in MOM6. I will not go into details. I'll let you guys read afterwards, and then Peter will cover the parametrizations in more details. But we have a lot of choices for mesoscale eddies, for the surface boundary layer, submesoscale, shear mixing, shortwave penetration, bottom boundary layer, geothermal, internal tide-driven mixing. It's like compared to POP, like the options of parametrizations here are many more, and it keeps increasing because of this concept of open development. We benefit not just from what we contribute, but from also other centers and researchers contribute. Going back to the idea of built-in wet and dry, one of the things you can do with that is better represent, for example, the interaction between the ocean and ice shelves. Ice shelves, which are kind of the interface between the land, ice, and the ocean. So those platforms of ice floating on top of the ocean. With MOM6, the wet and drying is built in. So therefore, like you can see, there's an ice sheet here on top of the ocean. and slowly the ice sheet is melting because of the ocean is providing heat, and that place that used to be an ice sheet suddenly becomes the ocean. And it is nicely done in this model, which from other models this is a big problem. We don't include ice shelves in the workhorse configuration yet, but that's something we would like to go in the future, and very important for the climate system when doing the coupling between land ice and ocean. We have a functional release of MOM6 starting CSM 2.2. And by functional, we mean it works, but it has not been scientifically validated. I'm listing here the steps that you need to follow if you would like to start running MOM6 within CSM. On Cheyenne, that will be straightforward. And that's these instructions here are meant to work on Cheyenne. You can go on your own and try to reproduce what's in here. And I also put a link here to a full detailed description of how to do that. Again, do that on your own. If you have any questions, please feel free to reach out to me. Briefly, those are the comp sets that we support with MOM6. You should be familiar now with the concept of comp set. You can read on your own like what each of those mean. And again, if you have any questions, feel free to reach out afterwards. The grids used with MOM6, so we have basically 2 or 3 grids that have been developed now. The first one is what's using the workhorse of simulations with MOM6 is the GX06. Is a tripolar grid. It has 3 poles, so one on top of Russia, the other one on top of I think that's Canada, and then we have the one on the South Pole. So that's why it's called tripole grid, and that's the workhorse configuration now has a resolution of 2/3 of a degree in the horizontal, again with equatorial refinement up to 1/4 degree. We have already performed century-long integrations with CSM MOM6 in fully coupled mode, and I'm showing you here a plot on the right of the SST bias compared to the observations over the last 30 years of the simulation. And the bottom line is that as of now, is producing a climate with bias and drifts very similar to what we get with POP. We are very actively working on this configuration with other components towards CSM3. In addition to the global workhorse configurations and high resolution, we also have these alternative configurations with MOM6. The first one is the so-called coupled aqua rigid planets. So the left plot shows the aqua planet. So basically you have 2 caps on the poles and everything else is water. And the right plot shows the rigid case. So then you have only like a ridge that goes from north to south. And those are fully coupled simulations. And this was a contribution from a grad student, Xiaoning Wu, that was an ASP visitor. And she did that during her PhD. And for those of you interested, we can talk more. We are currently working to develop a more user-friendly way to come up with these idealized planet configurations or quasi-aquaplanet configurations. I already mentioned we have high resolution configuration with MOM6.2, and this is just to show is the same grid basically we use in POP and MOM. So the top panel shows that this is eddy kinetic energy in the POP model, and on the bottom, same grid for the MOM model, and you can see they are very similar. We also have the option to perform regional simulations with MOM6. So all of these are the same dynamical core that you can do all of these type of simulations within the same CSM sandbox. We have 2 working configurations, regional configurations at the moment, the East Tropical Pacific one that's led by Scott Bachman from NCAR, and the Caribbean Sea Gulf of Mexico configuration, which is led by a grad student from CU, Giovanni Seijo. In terms of resources, these are all the resources available if you're interested in working with the POP model. So go to the webpage, you have user guide. I didn't mention about the Marble configuration or the biogeochemistry. You will learn more about that tomorrow with Keith Lindsay. But no, the biogeochemistry model is coupled to the ocean model in a way. It's of course has been implemented for POP, and we're currently implemented for MOM. here's the documentation for the Marble documentation, and Keith will talk more about that. And there's a forum if you have questions on the POP model that I put the link at the bottom here. And the same type of resources for the MOM6. There's a wiki, how to get started, some overview, tutorials. We also performed a series of webinars in 2020 with a lot of talks, and those are made available on this URL as well. The documentation keeps expanding. There's packages for doing post-processing analysis. And also, if you have questions, there's a forum within the CSM website. These are the references, and I'm happy to take any questions. Thank you for listening. If you want to engage with the Ocean Model Working Group, here's the link. Feel free to go and subscribe, and you'll be receiving the emails from us.
Great. Thank you so much, Gustavo. If people have questions, please come to the mics. Obviously, a pretty complex thing to understand how the ocean models being run, and our movement from POP to MOM is like a big component of what we're doing as the efforts within NCAR. So, yep.
Yeah, I was curious, like I'm mainly using the atmospheric models, and it seems that, like, as you mentioned, in the weather scale, for the ocean, it's like less than 1 degree, but for the atmospheric model, it's mainly 1 degree. I was wondering, like, in the coupler, does that control these different resolutions and like consider this like interaction between the weather scales, or how does it work?
Yeah, so the way the coupler works, it up to now, like, it always uses the highest of the two resolutions to interpolate from one to the other, and then propagate that. So if the ocean is receiving flux from the atmosphere, the coupler will interpolate that flux into the ocean grid and then propagate. Now, very recently, we have a capability of combining the two grids. So it's we basically overlap. The coupler grid is a combination of the atmosphere grid and the ocean grid, and then we'll basically superimpose those on top of each other. So it's a higher resolution than both the ocean and the atmosphere, and that will improve the fluxes. I don't know what is the limitation of like not including this. Like, you might, for example, lead to not representing the winds very well near the land ocean boundary, for example, because of the different resolution. But with this new capability, this type of problem will go away. Does that answer your question?
Yeah. Thank you.
So in the atmosphere model, we learned the other day that they have these regional grids, like the continental United States grid, where they have high resolution over one area and very coarse resolution over other areas. I was wondering if something similar is possible within MOM, although I think you mentioned that grids are challenging in ocean models.
Yeah, so for both MOM and POP, we use the curvilinear grid. Is a structured grid, is not an unstructured grid. An unstructured grid is what allows one to do this type of refinement of going like 1 kilometer in one region and 10 kilometers somewhere else. The curvilinear grid or structured grid gives you some leverage on like changing the resolution a little bit. However, not to the point where you can do things like what they do with the unstructured grid. So the answer is no, we cannot do the same in the ocean model with the type of grids that we support right now.
Thank you.
Sorry, Gustavo, is there anything to do with ROMs and MOM coupling? Because I know like having the nested grid ability within POP was something that we were developing and going forward with. Is there an effort for going from MOM to ROMs?
So actually, MOM is now being used by the coastal community as a regional ocean model. There's over 20 people, researchers, NOAA and universities working on that. And there's a weekly meeting or bi-weekly meeting devoted just for regional MOM6 capability. So it's basically doing what ROMs is doing. It's not as wide as spread at the moment, but it's growing very rapidly. So soon, like you will be able within MOM6 to go from global to regional.
And is there going to be like nested or like coupled, like two-way coupled?
we, we would like to do that. We don't have as far as I know, that has not been put forth yet. Yeah, that would be awesome. It's a very challenging problem to do the two-way nesting.
Great, thanks.
That capacity for freshening or wetting of, I'm assuming that was around Antarctica, that simulation you showed. Does that improve historical sea surface temperature predictions, or what effect has that
Yeah,
had?
so that was an idealized simulation that I showed, which it was representing processes that happen around Antarctica, as you pointed out. However, none of the climate models have this capability enabled yet. So I cannot answer your question because we haven't done that yet.
Do you have a hunch as to if it would?
No, I think I can see how that would play a huge role in the formation of Antarctica bottom water and sea ice around Antarctica, and therefore things like overturning circulation. For surface temperature, I'm not sure. Maybe around Antarctica, but not much far from there. Like I don't see how that would affect the surface temperature. Is so given by the flux that you receive from the atmosphere. So it's like a couple problem between ocean and atmosphere mostly. The ice shelf, I don't think it would impact that. That's my guess.
But would it be beneficial for the ice shelves, like being able to model the ice shelf retreat or extension?
For the ice sheets, yeah, it would definitely be like things like sea level rise. Like this capability is a huge piece of the puzzle that we're missing now. Presently, we cannot account for the ocean melting, the ice shelves, and then the water coming back to the ocean at depth, and that feedback between the two components. But that's something we have. You guys will see, we have glaciologists in CSM, Gunter and Bill Lipscomb. They developed the community ice sheet model. So we're in a very good position to go after this problem and make it.
Right. And Bill will be presenting on ice sheets later in the week. So that's great. And I'm sorry for asking questions because this is all new to me as well. Watching this new ocean model come in, the new sea ice and new ice sheet properties. This is great. So thanks, Gustavo. Really great. All right. Well, we might have our second break now. We're about 5 minutes sort of over schedule. So let's come back at 15:15 and we'll have our applications talks. So thanks, everyone.